Welcome to Unacademy. Unacademy is the India's largest online learning platform. About myself, I G Venkata. I have total 16 plus years of teaching experience. So far I mentored more than 60,000 students for their GATE examination. At present, I am pursuing my PhD in JNTU, Kakinada. First we check how to get Unacademy learning app. Just go to Play Store in your device. Type this one, Unacademy learning app. Unacademy learning app. And click this button, install. By clicking on this button, it will install the Unacademy learning app. After that, it will show the different top educators which are available in Unacademy. So these are the few of the top educators, and here few more top educators available, few more. Okay, now recently January 18th we started two new batches. One batch for GATE 2023 people students, and another batch for GATE 2022 students. And in electrical stream as well as electronic stream, in both these streams these batches was started. For 2023, the name for this one is Vervi batch. It was started from 18th of January. And Spark batch for GATE 2022 students. Okay, this is a batch. So it is also started from 18th of January. Again, Vervi batch for EC students. Now it is for EC students for GATE 2023. So it is starting from 18th of January. Okay, these are the, you can view here some of the top educators which are going to handling the main subjects for this batch. And next, again, Spark batch for GATE 2022. It was also started from 18th of January. All these batches are in English language. Okay, so this is for electrical people. Now, to subscribe any one of this batch, just use my code VRAW10 during subscription. You get maximum discount. Now we check first of all what are the different engineering courses provided by Unacademy. Mechanical engineering it is going to provide, electrical engineering, electronics and communication engineering, computer science and IT departments, civil engineering, instrumentation, production and industrial, chemical engineering. These are the different engineering streams where Unacademy is going to provide courses. Now here two subscriptions in Unacademy. First one is a plus subscription, second one is a iconic subscription. First one is plus subscription, second one is iconic subscription. From both the subscriptions, student is going to get classes from India's best educators, and there are interactive live classes, okay, and structured courses and PDFs. That course is well structured and they provide a PDF material of that course, and live tests and quizzes. After completion of these live tests and quizzes, they are going to prepare a study planner for each and every student based on his performance in tests and quizzes. Okay, if a student follows that personal plan, study plan, then definitely student success in their examinations. Okay, any competitive exam you can take, he will success. Okay, so these are the importances for plus subscription and iconic subscription. So these two subscriptions are available for both GATE and engineering services. Okay, now we check the cost for each plan. Now if you take the plus plan, these are the costs. For 1 month subscription 5,500, 3 month subscription 13,750, and for 6 months 1 year 30,250 rupees, and 18 months 38,500, 24 months it is 44,000. Okay, and so by using my code VRAW10, you can get 10% discount. You get 10% discount. So the discount is after using my code for subscription, you get 10% discount. Now after this, cost is 27,225. Okay, my dear students, my suggestion is, without second thought, you can join in Unacademy. Why? Because okay, whatever the top institutions we have in our India, okay, the faculty all are from those top institutions. Okay, they have experience to handle these GATE and engineering services classes in their top institutions. Okay, most of the faculty. Okay, and most of the faculty are at the same time they are from IIT background. Okay, simple calculation. See, for 12 months subscription, they are charging 27,000 after using the code. Okay, so 12 months. So if you are attending 5 days per class, see, 4 weeks, 4 into 2, 8 days. 8 days you are attending per month in class, to class and outside. Okay, now every day, nowadays transportation is very important. Now every day it is going to be 200 rupees for transportation. Okay, if you are taking the food at outside, nowadays a cost of 1600. Okay, and food if you are taking outside, nowadays food is worst case 200 rupees per day. Now it is 800 rupees. Okay, if you add additional expenditures, it became 2000 rupees. So each month you are going to be spending 2000 rupees to attend GATE classes outside of your home. Okay, some institutions, some organizations. Now here, for 12 months, 12 into 2, 24,000. 24,000 only. So 24,000, you are going to paying 27,225. That means you are paying 3,225, the net amount, additional amount. So if you join some other institutions, you have to pay nearly 35 to 40,000 for 1 year course. Okay, and that one and this one, just you calculate. And the advantage of this one is you can stay at your home. Okay, and there you are going to saving, more importantly, you are going to saving the time. No need to travel anywhere. Okay, so that is my suggestion to students. Now this is about your plus plan, and the next one is we are going to iconic plan. In iconic plan we have only two subscriptions. One is a 12-month subscription, the second one is a 24 months subscription. Okay, in 12-month subscription it is going to be 50,250 rupees they're charging. Okay, and by using by availing the subscription code, by availing my subscription code VRAW10, you get 5% discount. After that the cost is 45,225 rupees. Okay, so this is about both the plans, plus plan and iconic plan. Okay, now I'm going to topic. Now today's topic is Fermi Dirac Distribution function. What is this Fermi Dirac Distribution function? Okay, where we are using this? Okay, is this function is applicable to the electrons what we are using? See, by using this function, we can investigate the distribution of carriers over the available energy states. Once again I am repeating, sir. One can investigate the distribution of carriers over the available energy states. So these are the available energy states. Now whatever the carriers you have, you are going to be distributing those carriers here. That is the FDD. Okay. Here FDD is defined by an equation, that is f of E is equal to 1 by 1 plus e power e minus ef by kt. So once again I am writing the same equation. See this, f of E is 1 by 1 plus e power e minus ef by kt. So that is the equation for FDD. In this, E is the, here E what we have, that E is the energy level or energy, EF is Fermi energy, and K is Boltzmann's constant, and T is absolute temperature. And the units for K and its value is, it is defined in two ways, either joule per Kelvin or electron volt per Kelvin. Already yesterday's class we discussed, we related joule and electron volt. Okay, so now in terms of joules and Kelvin, it is 1.38 into 10 power minus 23 joule per Kelvin. In terms of electron volt per Kelvin, it is 8.62 into 10 power minus 5 electron volt per Kelvin. Okay. Now the most important thing is f of E. What is f of E? That is very, very important. So simply f of E is a probability function. Okay. Once it is probability function, you said its value is greater than or equal to 0 and less than or equal to 1. So its value is in between 0 to 1. Probability function is, any probability value is, maximum value of probability is 1. So its value is in between 0 to 1. And it is represented as probability that an energy level E occupied by an electron. Once again I am repeating, sir. Probability that an energy level E occupied by an electron. Okay. Probability that an energy level E occupied by an electron. See, most of the students are not understand what is this. What is the meaning of this? I will explain that. For this, I am going to taking 10 electrons. Let us assume 10 electrons. Here is one electron. Here is second, third, fourth, fifth, 5, 6, 7, 8, 9 and 10. 10 electrons here I taken. Okay. Now the most important thing is, I am going to defining an energy level somewhere here. This is a defined energy level. Now, what is the probability that the energy level E occupied by an electron? See, E or more than E. See, how many electrons occupied this energy level, minimum this energy level? See, 1, 2, 3. These 3 electrons, energy is more than E. This is the increasing order of energy. Okay, so these 3 electrons, energy is greater than E. Now, total number of, now I am writing probability function f of E value. So, probability, how you are writing probability? Total events by favorable events. Total events are 10. That means total electrons here we have 10. Okay, 4 plus 3 is 7 plus 3 10. Now 10 and favorable events. How many electrons are crossing that level? Here 1, 2, 3. 3 electrons energy is greater than or equal to E. Now it is 3 by 10. This is the probability function. That is the meaning of it, f of E. Probability that an energy level E occupied by an electron. Okay, I think so, my dear students, you get clear picture about f of E. Okay, most of the students are not understanding that what it is. Okay, so this, from this example, I think so all of you are get clear information about this. Now see this 3 by 10, it is 0.3, so it is less than 1. Okay, that is the f of E. Now first I am going to taking f of E at for t at t is equal to 0 first. At t is equal to 0, what is f of E? Okay, now see this. This is our function. F of E is equal to 1 by 1 plus e power e minus ef by kt. Kt, e minus ef by kt. Here, now I am taking the condition let t is equal to 0. Let t is equal to 0. Once t is equal to 0, that means at t is equal to 0, you can take two conditions. Here, E minus EF is greater than 0 or less than 0. That means either E is greater than EF. This is one possibility. Okay. And second possibility is E is less than EF. For E greater than EF, for E greater than EF, E minus EF is positive. Okay, and for this E minus EF is negative. E minus EF is negative. Okay, and after that, now I am going to substituting these values here. So now f of E became 1 by 1 plus e power E minus EF is positive by T is equal to 0. Temperature T is equal to 0. Same thing I am writing here. F of E became 1 by 1 plus e power negative, because E minus EF is negative, by 0. Now its value is 1 by 1 plus e power, it is minus infinity, and its value is 1 by 1 plus e power plus infinity. Okay, so we know that e power plus infinity is equal to 0 and e power minus infinity is infinity. Just substitute that values here, is infinity. Substituting that values here, now f of e became 1 by 1 plus e power infinity is 0. So that is 0. Now it is 1 by 1, which is 1. There is a much meaning in this. F of e equal to 1 in this sense. There is a much meaning involved in that. Later we verify that. Now after this, e minus infinity is infinity. Take this one, substitute here. Then you get f of e became 1 by 1 plus e power minus infinity is infinity. Something by 1 plus infinity became 1 by infinity, which is 0. Okay. So now whatever the data, final data I got, I am going to placing those two in a single slide. Okay. See here. Now, first condition at t is equal to 0, we got taken two conditions. First condition is e greater than ef, e greater than ef. Okay, in e greater than ef, we got f of e became 0. And in second condition, we taken e less than ef. So here f of e became 1. Okay, so just once again check this. See, for e greater than ef, f of e greater than ef. Sir, just a minute, sir, sorry. Sir, e power minus infinity is 0, sir. It is 0. Sorry, it is 0 and it is infinity. Sorry, small confusion. Now, you can substitute the value. Now, see, once it is 0, okay, now it became 0. So f of e is 1 by 1 plus 0. So that is 1. And here it is 1 plus e power plus infinity is infinity. So it is 1 by infinity, it became 0. Sorry, a small confusion. Okay, now finally for e less than ef, it is 1. For e greater than ef, it is 0. Now for e greater than ef, it is 0. For e less than ef, it is 1. Okay, now I am going to plot this f of e and e. So here it is going to be a plot between energy and f of e, probability function. Energy and probability function. So f of e is having maximum value of this is 1. So it is 0. It is 1 by 2. And let us take it as 1. So maximum value. Now here we are comparing the energy with ef. So somewhere here I am going to taking ef. Somewhere here it is ef. Now once you decided ef, based on that I am going to dividing that into two parts. During this region your e value is greater than ef. So e is greater than ef. And during this region e is less than EF. For E less than EF, E less than EF, f of E value is 1. So here f of E value is 1. And here f of E value is 0. We get 0. Now I am placing these things here. So up to here it is 1. Now from this it is 0, 0. Now this is fixing. Yeah, this is the plot. This is the case at T is equal to 0. That is very, very important. At 0 Kelvin. Okay, at 0 Kelvin. Now, here, next I am going to taking the for T not equals to 0 and at E is equal to EF. E is equal to EF. So our equation for f of E is 1 by 1 plus so 1 by 1 plus E power E minus EF by KT. Okay, here I am taking K not equals to 0, but E became EF. Now f of EF became, that means I am going to replacing E by EF. EF equal to 1 by 1 plus E power EF minus EF. EF minus EF by KT as it is. So it became 1 by 1 plus E power EF minus EF is 0 by KT. So that is it became so here it is 1 by 1 plus E power 0 by KT, it is E power 0. So that is 1 by 1 plus E power 0 is 1, which is 1 by 2. So at E is equal to EF, at E is equals to EF, for T not equals to 0, it became 1 by 2. Okay. Sir, is it okay? Now, I am going to varying the temperature. I am going to taking different temperatures. Once we take the different temperatures, what we get? And before going to that, at 0 Kelvin, we got this plot like this. So what is the meaning of this plot? What is the meaning of this plot? What we can understand from this plot? Okay, now I'm going to check this. Sorry. See, this is the thing we calculated. Probability is 1 by 2 so far we calculated. Okay, that means at E is equals to EF, we get probability is 1 by 2. That means EF is the average energy level occupied by an electron. Okay, and EF is the maximum energy level occupied by an electron at 0 Kelvin. Sir, it was given in previous GATE examination. This point, the maximum energy level occupied by an electron at 0 Kelvin is Fermi energy level EF. Okay, and the probability of finding an electron at EF is 1 by 2. That means it is the average value. So EF also called as average energy level occupied by an electron. Okay. Now from this, what we understand, say this. This is the plot we get so far at 0 Kelvin. Energy F of E, its value is here 0, So here it is 1 by 2 and here it is 1 and here is EF, Fermi energy level. Okay, now what I am doing is at 0 Kelvin, whatever the energy band diagram we have, I am going to taking that energy band diagram. Here I am taking intrinsic semiconductor. So this is the energy band diagram. Now this is EV and it is EC. This is a conduction band and it is valency band. And we observed already at 0 Kelvin, all covalent bonds are completely filled. All covalent bonds are completely filled. The meaning of this one is, initially while discussing about energy band diagram at 0 Kelvin, that means at their interatomic distance, standard interatomic distance, the total energy level is split into two equal halves. Okay, split into two equal halves. Okay, upper 4n energy levels and lower 4n energy levels. At 0 Kelvin, available 4n electrons occupy all available lower 4n energy states. So all these energy levels are occupied. All these energy levels are occupied. No empty energy level is available in valency band. That is the meaning of this. Because of that, you get here probability 1. Probability 1 means all are occupied. All n electrons, whatever the 10 electrons you given, all these 10 electrons are above the defined energy level. That is the meaning of that. Okay. If energy is less than EF, if energy is less than EF, less than Fermi energy level, okay, less than Fermi energy level, all energy levels are occupied by electrons. That is the meaning of that. And after this EF, for E greater than EF, probability 0. That means no energy level is occupied. No energy level is occupied. Here probability is 0. Here probability is 1. Okay, that means you can take approximately EF value somewhere here. And one more important thing, sir, please remember, FDD is applicable to only defined energy level regions. Okay, here this is our energy gap. This is energy gap. Energy gap. Okay, here energy gap in the sense no energy level is defined in energy gap. Okay, no electron is going to occupying the energy level in energy gap. So that is, so FDD is not applicable to that energy gap. Not applicable to energy gap. Okay, it is applicable to only valency band and conduction band. While discussing about Fermi Dirac distribution function, you have to think your energy gap, or you can omit the energy gap. By omitting energy gap, you can think of it. Okay. So at 0 Kelvin, all energy levels less than EF, less than Fermi energy level are completely filled. And at 0 Kelvin, we mentioned valency band is completely filled and conduction band is completely vacant. This is the meaning of this. Completely vacant in this sense, its probability is 0. Here its probability is 1. That is the meaning of this. Okay, sir. Is it clear? Now, I am going to increasing temperature. For my better understanding purpose, I am going to removing this. Okay, now, and at the same time, your energy band diagram is like this. For my better understanding purpose, I am going to be this is rotating like this, rotating clockwise. Now, this is my energy band diagram. So EF. Let us assume it is EF. Now below this, all energy levels are occupied. All energy levels are occupied. That means all covalent bonds are completely filled. So this is similar to valency band. So here all energy levels are occupied. That means all covalent bonds are completely filled. All covalent bonds are completely filled. Next one is yeah. Okay, now next one is E greater than EF. No energy level is occupied. Here no electron is available. That means it belongs to conduction band. Okay. Now I am going to increasing the temperature. Now this is the case at T equal to 0. Now I am going to taking temperature T1 Kelvin and T1 is greater than 0 Kelvin. Once increasing temperature, here whatever the covalent bonds close to the valency band, these covalent bonds will break first, and most of these covalent bonds will break and electron is moving away from the valency band to conduction band. We know that. So it is moving. See, this is moving. Here it is occupying this. Here it is occupying. Here it is occupying. Okay, most of the covalent bonds close to the EV are going to be breaking. At the same time, few of the covalent bonds less than this, little bit away from the EV are also breaking. This is also breaking, but they are less in number. Less in number. And like this. And after this, one covalent bond from here is going to be breaking. Now here occupancy point of view, in this most of the electrons are going to occupy the energy level just above the conduction band, and few electrons occupy the energy level greater than this and few electrons greater than this. Okay, the way how going below the valency band is in a similar way, energy level occupying above the conduction band. Here, see. So here most of the covalent bonds are breaking. Most of the energy levels are vacant. Here little bit covalent bonds are breaking. Here very few covalent bonds are breaking. Now once covalent bond is breaking, electron is moving from here to here. Once electron is moving, it became a vacant position. Now here there is no electron. No electron is available here. Okay. Now here more electrons are going to be occupying. Initially probability here probability of occupancy is 0. Now here electrons are going to be occupying. Here electrons are going to be occupying. Now I am representing that one by like this. Okay, next level of electrons occupancy, blue color. Now next level of occupancy, this much. Next level of occupancy by green color, less. Okay, our total probability function is 1. Now at t is equal to 0, t not equal to 0, e equal to ef, it is 1 by 2. Now this is 1 by 2, but this is less than 1 by 2. Less than 1 by 2. Okay, so let us take it is the probability 0.4, and let us take it is 0.2 or 0.3, and it is 0.1. After that it is 0. That means this is the probability of occupancy of the energy levels in conduction band. That means for energy greater than EF. The same way, if you go to this vacant energy level, here most of the covalent bonds will break close to the here. most of the covalent bonds will break. Okay, now let us take this much number of covalent bonds are breaking. This much number of covalent bonds are breaking here. And here this much covalent bonds are breaking. Here this much number of covalent bonds are breaking. See, this much is breaking in this sense. This much is breaking. That means this much is occupying. So once a covalent bond is breaking, electron is moving from valency band to conduction band. I will show that one here. Listen carefully, sir. It is very, very important, sir. Based on this knowledge, you can estimate the Fermi energy level of a semiconductor. Any semiconductor you can take. Based on the doping, you can estimate the Fermi energy level position. Let us take this is a EC and it is EV. Now, if I am taking, for my better understanding, I am taking only two atoms, two covalent bonds here I am representing. Once increasing temperature, this covalent bond is breaking, electron is moving from here to here. Now, so let us electron is moving here to here. The meaning of this one is this energy level, here it is covalent bond is filled. That means the energy level what you defined here is occupied by this electron, and the energy level what is present here is vacant. This is vacant energy level. Okay, that is the vacant energy level. This is occupied energy level. This is vacant energy level. And now this electron is moving from here to here. This electron is going to occupy some energy level here. This energy level is occupied by this electron. So these are the once covalent bonds are breaking, electrons moving from conduction band to valency band. After moving, most of the electrons occupy the energy levels close to the EC. By moving away from the EC, occupancy is going to be decreasing. Similarly, vacant energy levels, vacancy, that means breaking of covalent bonds. The covalent bonds which are just below the EV, most of the covalent bonds just below the EV are breaking. Okay, by moving away from this, the breaking is going to be decreasing. Breaking, decreasing. Covalent bonds number breaking, decreasing in this sense. Occupancy is increasing. Okay, if you want a clear picture, now let us take EV. Okay, so here I will write occupancy. Here I will write this side, I will write breaking. Here it is breaking, I am writing. And this is, don't forget, it is EV and it is EC. Let us 10 covalent bonds here. Now increasing temperature. Let us take total 10 covalent bonds. Let us 10 covalent bonds. Here 10 covalent bonds. 10 covalent bonds. So here also 10 covalent bonds. For in each row you can assume 10 covalent bonds. Now let us, by increasing temperature, here breaking, 8 covalent bonds were broken. So once 8 covalent bonds were broken, here occupancy is only 2. 2 energy levels are occupied. 2 energy levels are occupied. Next, here in the second case, 6 covalent bonds were broken, and here occupied is total 10. 10 minus 6, 4 occupied. Next, 4 covalent bonds were broken, 6 occupancy. Now 1 covalent bond were broken, 9 occupancy. Okay, by moving away from the EV, that means by moving this side, probability of occupancy is increasing. Okay, so and anything you may follow one thing, at E is equal to F, it should be 1 by 2. Now see, by moving away from it, that means at this edge of the semiconductor, no covalent bond is breaking. So at this point, probability of occupancy is full. Now 0 breaking, complete 10 occupancy. 10 energy levels are occupied by 10 electrons. Now here it is 1 probability. By moving away from it, that means by moving towards this side, breaking is increasing, occupancy is decreasing. That means probability of occupancy is decreasing. So probability is decreasing. But anyway, at E is equal to EF, it became 1 by 2. Now after this, probability of increasing, it is occupancy is here, occupancy initially 0 at T equal to 0. Now few electrons occupied here, probability of occupancy going to be decreasing like this. This is the case at T1 Kelvin. For example, I am going to taking another temperature T2 Kelvin. That is, T2 is greater than T1. In that case, it just add 1 to this. 1 plus 1. Now here one covalent bond is breaking. Okay, here one covalent bond is breaking, here 0 covalent bonds, here 2, here 5, here 7, here 9. Simply the plot is moving downwards. But anyway, it is going to follow this. And here once it is decreasing, here it became increase like this. This is for T2 Kelvin. That is for T2 Kelvin. Okay. Now from this, once temperature is increasing, probability of occupancy for energy level greater than EF is increasing. For energy level less than EF, probability of occupancy is decreasing. Okay. Now we are going to using this knowledge to estimate the Fermi energy level of a semiconductor. You can take any semiconductor, it may be intrinsic, extrinsic, whatever it is. You are going to be using that. Okay. Now, okay, before going to that, let us we solve this problem. See, show that you have to show this. Show that the probability of a state delta E above EF, is filled equals the probability that a state delta E below EF is empty. It is empty. Okay. Now, just a minute. Here, see one thing, sir. This is total 1. This total value is 1. Let us take this is a point. It is 0.5. It is 0.7. It is 0.7. Sorry. This is 0.7. That means it is 0.7. Now once it is 0.7, it became 0.3. And you are saying this is probability of vacancy. Probability of vacancy. Okay. This is very important, sir. How to represent f of E? Occupancy, vacancy. Simple. This is 1 minus this value. Okay. So just 1 minute, I will restart this. There is some issue. Yeah. Now here this is f of e, this is e, and it is ef. So the maximum value of f of e is 1. Somewhere here it is 1 by 2, it is 0. At 0 Kelvin we plot it, we plot like this. Like this. Now let us, I am taking the temperature T1. At temperature T1, my plot is like this. So it is like this. So this is the f of e plot. Just I am going to only keeping this plot. I am going to erasing that for better understanding. Yeah. Now, so f of e value, let us take this point. 0.7, let us assume. So f of e means probability of occupying an energy level E by an electron. So always f of e means probability of occupancy. F of e is, let us take 0.7. This is probability of occupancy. Probability of occupancy. Okay, now, so once you are placing some one energy level in this sense, it should be occupied by electron or it should be free. Only two possibilities. Once you are defining some energy level, it should be occupied by some electron or it is vacant. Okay, so only two probabilities, either occupying probability or vacancy probability. Okay, now this is going to be this is 0.3 because it is 1, it is 0.7, 0.3. Okay, so 0.7 I am writing it as 1 minus 0.3. So this is probability of occupancy, means this is going to be probability of vacancy. So 1 minus probability of vacancy. Probability of vacancy. Now this is nothing but your f of e. Now just take this one this side and this one this side. Now therefore finally we can conclude that probability of vacancy is equals to 1 minus probability of occupancy, 1 minus f of e, 1 minus f of e, that is. So f of e is nothing but a probability of occupancy. Therefore probability of occupancy plus probability of vacancy is equals to 1. So probability of occupancy plus probability of vacancy is equals to 1. So this is very, very important, sir. Okay, now we go to that problem. Based on this, we solve that. So vacancy is 1 minus f of e. Okay, next slide. Yeah, now show that probability of a state delta E above EF, delta E above EF is filled. That means occupied, means we need f of E. F of E. Here it is empty. Empty means vacant. Vacant. So here we need 1 minus f of E. Okay. Now they are saying both should be equal. You have to show that. That is the thing you need to show. First of all, I am going to taking filled level. Filled. Next I go to vacant. First of all, I need to define that energy level. This is the regular thing we defined already. This is the plot what we have already. F of E and E. So its value is 0, 0 and 1. So ideal conditions, that means at 0 Kelvin it is 1 at EF. So for T, this is for T 0 at 0 Kelvin. At 0 Kelvin. For greater than 0 Kelvin, your plot is like this. Like this. Now here they are going to saying the state delta E above EF. Above EF, delta E state. So this is delta E. Delta E. At this point, probability of occupancy is this much. Now the point here, energy. This energy is don't get confused, sir. This is EF energy. Now at this point we need, that is, this is a delta F and this is going to be delta F. Delta E. Now it is here energy is here. The E value is here EF plus delta E. EF plus delta E. At this point, I want the probability of occupancy. So therefore, F of, this is our equation, standard equation. So our standard equation is F of E is equals to 1 by 1 plus E power E minus EF by KT. Now, filled means, so I am taking at E is equals to EF plus delta F. Plus delta F. Sorry, delta E. EF plus delta E. Now, the condition is at E is equals to EF plus delta F. Sorry, delta E. Sorry. E is equal to, now I am going to substituting in place of E this much, EF plus delta E. So which is 1 by 1 plus E power E. E is nothing but a EF minus EF plus delta E. EF plus delta E. Okay, minus, here is EF. EF. Okay, now by KT as usual, by KT. So here this EF gets cancelled. Now it is 1 by 1 plus e power delta E by KT. 1 by 1 plus e power delta E by KT. So this is the probability of occupancy or probability of filled at a energy level E greater energy level delta E above the EF. Okay. Next I am going to probability of empty energy level at EF below the EF. Sorry, delta E below the EF. Somewhere here. It is E. Now it is, let us take it is a delta E. This difference is a delta E. Delta E. Now here it is probability of vacancy. This is probability of occupancy here to here. F of E value you are getting. 1 minus this value is probability of vacancy. So this is going to be F of E. This is EF. This is less than delta E. So EF minus delta E. Delta E. EF minus delta E. This is probability of occupancy. At energy level, EF delta E less than EF, and probability of vacancy is this much. This is going to be 1 minus F of EF minus delta E. Okay. So in next slide, I will write that in detail. Sorry. Next. So now it is. So previously we get now F of EF minus delta E is equals to probability of occupancy, probability of occupancy at E is equals to EF minus delta E, and 1 minus F of EF minus delta E is equals to probability of vacancy at E is equals to EF minus delta E. This is we need. Okay, now first I am going to calculating this. Therefore, F of EF minus delta E is equals to, our standard function is 1 by 1 plus e power EF minus E. Okay, sorry, E minus EF. So I am writing our function once again, don't confuse. E is 1 by 1 plus e power E minus EF by KT. Okay, now here E value is this much, EF minus delta E. Now I am substituting that. E value is EF minus delta E minus delta E minus EF value here we have. So EF by KT. So here this EF and this EF gets cancelled. which is 1 by 1 plus e power minus delta E by kt. But we need 1 minus this much. Therefore, 1 minus f of Ef minus delta E equals to 1 minus this value 1 by 1 plus e power minus delta E by kt. Just to simplify this, now it is 1 plus e power minus delta E by kt minus 1 by 1 plus e power minus delta E by kt. Now these two gets cancelled, and in denominator just take e power minus delta E by kt common. Now that one and this one gets cancelled. Finally it became 1 by 1 plus, once you are taking this one common, it became e power delta E by kt, and it became 1 plus e power delta E by kt. So this is the value finally you got. This is the probability of vacancy. So probability of vacancy you got 1 by 1 plus e power delta E by kt. Probability of vacancy. Now probability of occupancy you got already, you calculated, that is it was 1 plus e power delta E by kt. Same thing, just I will show that one to you. See this, here we calculated probability of occupancy 1 by 1 plus e power delta E by kt. Okay, so see here, probability of occupancy and probability of vacancy at a distance equal away from the EF are same. There you observe in that plot they ask at a distance at an energy level delta E above the EF and at a distance delta E below the EF. That means they are moving equally away from the EF, both the sides. Okay, so that is the solution for this, just to be shown that. So for engineering service point of view, this type of problem, so you should practice. Okay, so next, yeah, now I'm going to take another problem here. See this, determine the probability of occupancy of following energy levels at 0 Kelvin, 300 Kelvin and 600 Kelvin. Sir, they are asking only probability of occupancy, only occupancy. Occupancy means we need f of E. Vacancy means it is 1 minus f of E. We need only f of E. Okay, so in first case, in this case, let us take A bit. In this case, energy is 0.2 electron volt above EF. That means E is equals to EF plus 0.26 electron volts. Okay, in B bit, in case of B bit, for this 26 electron volts below EF. So here E is EF minus 0.26. C bit 0.52 electron volts above EF. E is equals to EF plus 0.52 electron volts. And next D, E is equals to 0.52 electron volts below EF. 0.52 electron volts below, that means EF minus 0.52. Okay, so we have a standard equation for f of e. So our equation for f of e is 1 by 1 plus e power e minus ef by kt. Now here in place of e, just you substitute this value, this one, this one, this one, this one. So I am doing the same. Now here f of e means ef plus 0.26 electron volts is equals to 1 by 1 plus e power, e means ef plus 0.26, ef plus 0.26 minus ef by kt. So by simplification you get ef gets cancelled. It is 1 by 1 plus e power 0.26 by kt. Here also I am doing the same thing. Here now you get f of e minus ef minus 0.26 is equals to 1 by 1 plus 1 by 1 plus e power, it is minus. See here, once you get plus, that's why we got plus. Here we have negative, minus. So you get minus 0.26 by ef, sorry, by kt. Similarly here, f of ef plus 0.52 electron volts equals to 1 by 1 plus e power, it is plus. So this ef and here ef gets cancelled, 0.52 by kt. Similarly, you can write same equation here, you get e power minus 0.52 by kt. Just to simplify that. Now this is for occupancy. Let us take vacancy also. For vacancy our requirement is that is occupancy. Okay. Next I am going to vacancy. Vacancy equals to, vacancy is equals to 1 minus f of e. In first case, for a bit, answer is vacancy is 1 minus 1 by e power, sorry, 1 plus e power 0.26 by kt. For b bit, vacancy is 1 minus 1 by 1 plus e power minus 0.26 by kt. Similarly, for c bit, vacancy is 1 minus 1 by 1 plus e power 0.52 by kt. Next, for d bit, vacancy equals to 1 minus 1 by 1 plus e power minus 0.52 by kt. Okay, now the value what you are getting in option A, previous case, and the value what you are getting here, both are equal. You get both equal. Here this one and previous b bit both will equal. Here this one and previous c both are equal. D both are equal. But in your problem they given at a temperatures of T is equal to 0 Kelvin, 300 Kelvin and at a 600 Kelvin. Just substitute the K value. Okay, K is Boltzmann constant. And now one more thing, I need to tell something about K value. Just take a look of this. KT value. K is a Boltzmann constant. Okay. At T is equals to 300 Kelvin, KT value is approximately 26 milli electron volts. KT value is 26 milli electron volts or 0.026 electron volts. You get approximately 0.02583. Okay, so approximate we can take it as a 26. Okay, this is the K value. Next, so this is your problem. Just to substitute the different temperatures in place of T. Okay, you get substitute K value and temperature value, you get it. Okay, next one is, it's over already. So now applying FDD, that means Fermi Dirac Distribution function, to semiconductors. By applying this, I am going to identifying Fermi energy level of a semiconductor. Okay. First of all, I am applying this one to intrinsic semiconductor. First applying to intrinsic semiconductor. Before going to that, you should know the energy band diagram of that intrinsic semiconductor and number of charge carriers available in that. Okay, so this is the energy band diagram of intrinsic semiconductor. EV and it is EC. In this, number of electrons is equals to number of holes is equals to Ni. We know that. That means electron concentration is equals to hole concentration. Electron concentration is equals to hole concentration is equals to Ni, intrinsic carrier concentration. Okay. Now, electron concentration. Just observe electron concentration. Now, electrons are available in conduction band. That means electrons are going to occupying the energy levels in conduction band. Okay, now holes. Holes are vacant energy levels in valency band. Holes are vacant energy levels in valency band. So electron concentration equals to hole concentration in the sense, here number of electrons occupy the energy levels is equals to number of vacant energy levels available here. Now that means probability of occupancy here in conduction band is equals to probability of vacancy in valency band. Probability of occupancy in conduction band is equals to probability of vacancy in valency band. And here F of EC means probability of occupancy in conduction band. Occupancy, it represents electron concentration. If electron concentration is more occupancy is there. That means probability of occupancy is close to 0.8, 0.9 like that. Occupancy in conduction band. So that is the probability of occupancy in conduction band. Next one is F of EV. This is also probability of occupancy in valency band because it is EV. Okay, why? Because to get the but I want vacancy. To get the vacancy, first I know the occupancy. Okay, so this is probability of occupancy. Occupancy. Now 1 minus f of EV is probability of vacancy in valency band. Probability of vacancy in valency band. Okay. Now, in intrinsic semiconductor, you are saying N is equals to P is equals to Ni. That means electron concentration equal to hole concentration. So, probability of occupancy f of EC is equals to probability of vacancy 1 minus f of EV. Okay, in n-type semiconductor, electron concentration is more. That means f of EC is greater than 1 minus f of EV. And next, in p-type semiconductor, hole concentration is more. That means f of EC is less than 1 minus f of EV. Okay, now this is the basic information we need. So based on this information, I am going to writing the energy band diagram. Okay, so okay, now here I am going to first applying that one to intrinsic semiconductor. Intrinsic semiconductor. Semiconductor. Okay, now here we know electron concentration equal to hole concentration. It means f of EC is equals to 1 minus f of EV. Probability of occupancy in conduction band equals to probability of vacancy in valency band. Okay, and we know one more thing, because we are taking electron concentration some hole concentration in this sense. This is a default at room temperature, sir. Please keep that in your mind. So once it is room temperature, that means T not equals to 0. Okay, once T not equals to 0, we have a condition for T not equals to 0 Kelvin at E is equals to EF, F of EF became 1 by 2. Sorry, okay, F of E is equals to 1 by 2. Just write E, that is sufficient. E is equals to 1 by 2. Okay, now based on this information, I am going to representing the energy band diagram. Okay, so now here I am going to plot a graph between f of E and energy. On this axis, this direction I am taking energy. Okay, and this is the another one. Now in this direction I am going to taking f of E. So this is energy you are saying. Okay, we have two energies, EC and EV. This is EC and this is EV. EV. Okay. Now, this is f of e, you are saying. F of e is the probability function. Okay. So, this is increasing in this direction. So, its value is 0 at this point, and the maximum probability is 1 here, and at somewhere here it is 1 by 2. 1 by 2. Just I am dragging that one here. Now, so you need to start the occupancy from this side. Okay. So first, so for intrinsic semiconductor, you are saying f of EC. So f of E is moving this side. Now this is EC. Now this is f of EC. F of EC is this one, and equals to 1 minus f of EV. From here to here it is f of EV, and here to here it is 1 minus f of EV. F of EV. So this is f of EC, and this is 1 minus f of EC, sorry, EV, 1 minus f of EV. Both are equal. To align these 2 points, I am going to plotting it. So it is moving like this, like this. So it is like this. Just I am going to be right like this. Now this plot is going to be this at this point, at that point, what happened is f of e became 1 by 2. But f of e is 1 by 2 is nothing but at an energy of ef, it became 1 by 2. So this is the, just I am extending this. Now this is going to be the Fermi energy level of intrinsic semiconductor, EFI. EFI means Fermi energy level of intrinsic semiconductor, EFI. Okay. Now, if you observe this, it is approximately midpoint of the energy gap. Midpoint of energy gap. Approximately, not exactly. There is a condition required to make that exactly midpoint of energy gap. Okay. While solving problems, you can treat EFI is midpoint of energy gap approximately. At that time, they will ask calculate the particular value approximately, or what is the approximate value of, okay, Fermi energy level position, or energy level below the conduction band, below the above the valency band, like that. Once they use the term approximate, you can take EFI is a midpoint of energy gap. Otherwise, you don't take. Okay. So finally, from this, Fermi energy level of intrinsic semiconductor is approximately midpoint of energy gap. Now this is the complete energy band diagram of a intrinsic semiconductor. So in intrinsic semiconductor, here it is EC, here we have EV. So in between we have EF, Fermi energy level. So to specify or to identify it is intrinsic semiconductor, I am adding a subscript I to that. EFI. EFI is the intrinsic Fermi energy level. Okay. Later we derive an equation for this EFI in terms of EC and EV. Okay. Later. This is about intrinsic semiconductor. Finally, in intrinsic semiconductor, Fermi energy level is approximately midpoint of energy gap. Next I am going to taking n-type semiconductor. Second one is n-type semiconductor. In n-type semiconductor, what we have is electron concentration is more compared to hole concentration. If you want to say strictly, electron concentration is much more. In regular practical point of view, electron concentration is much more compared to hole concentration. Now, it means F of EC, that means probability of occupancy, is much more compared to probability of vacancy, 1 minus F of EV. Okay, let us take 1 greater than is sufficient here. So this is greater than. Okay. Now, and we know that at E is equals to EF, it is fixed. F of E became 1 by 2. E became 1 by 2. Now I am placing all these things in a plot. So this is on this axis. I am going to take the energy. Okay, you can take do one thing. I am following the previous procedure. Okay, here, okay, you can take either positive direction or negative direction. It's not an issue. Okay, so this is energy, and in this direction I am going to taking the F of E value, F of E value. So now it is so like this. Now here this is going to be EC and it is going to be EV. So F of E value, this is starting point, so it is probability is 0 here. Here probability is maximum 1 by 1. Here it is center 1 by 2. Okay, so for my easy understanding I am going to just extending this. Yeah, now next one is F of EC. So I am starting from this side. Now this side we are starting from this side to this side, moving. So F of EC is greater than. So this is F of EC. F of EC is greater than 1 minus F of EV. From this side F of EV. So this side 1 minus F of EV. This is 1 minus F of EV. So first I am representing this. This is 1 minus F of EV, probability of vacancy in valency band, and this is F of EC, probability of vacancy conduction occupancy in conduction band. Now I am going to drawing an imaginary line to map these two. Imaginary line like this, like this, like this. Now here this imaginary line at this point, its probability of occupancy is 1 by 2. Now I am going to be extending this line horizontally. This is Fermi energy level of n-type semiconductor, EFN. Now EFN is close to the conduction band EC energy level. Okay, so in a semiconductor, if you are increasing n-type impurity, Fermi energy level is moving towards conduction band. These points were asked in previous GATE examination, sir. Okay, and you can expect problems on this energy plot also. Okay, so if you complete the energy band diagram of this, it is like this. For n-type semiconductor, energy band diagram is like this: EC, EV. Now this is EFN. Okay, for reference purpose you can keep EFI also on this. EFI is approximately midpoint of this. EFI. Okay, so in examination you can expect a question on this energy band diagram, energy band. They may ask any difference. Either they may ask EC minus EFN, or EFN minus EFI, or EFI minus EV, or EFN minus EV. You can expect any question. Okay. But they give only few amount of data. Okay. Now, this is about your N type. Next, I am going to P-type semiconductor. I am going to P-type semiconductor. So for P-type, we know that third one is P-type semiconductor. P-type semiconductor. So we know that in P-type semiconductor, hole concentration is much greater compared to electron concentration. That means probability of vacancy in valency band 1 minus f of EV is greater than probability of occupancy in conduction band 1 f of EC. And we know that at f E is equals to EF, f of E became 1 by 2. So similar to previous case, I am going to plot it. This is the energy, and in this direction I am going to taking the f of E probability function, and here this is the plot. Yeah, it's good. Next one. Now, yes, here this is E EV and EC. Okay, so I'm writing EV here. So f of E value 0 at this end, it is 1 at this end. Now at center it is 1 by 2. Just extending this for our easy analysis purpose. Now f of EC from this side, it is f of EC is less. So f of EC is less. This is f of EC, and 1 minus f of EV is more. So from this side f of EV, from this side 1 minus f of EV, it is more. So here it is 1 minus f of EV, and here it is f of EC. F of EC. Now I am going to combining this through an imaginary line. Yeah, at this point, its f of E became 1 by 2. Now just I am going to drawing an horizontal line. So this is going to represent the Fermi energy level of P-type semiconductor, EFP. EFP. So from this what we observed, by increasing the amount of P-type impurity, by increasing the amount of P-type impurity, Fermi energy level is moving towards valency band. Towards valency band. Now I am going to complete energy band diagram of P-type semiconductor. and so this is EF at center approximately. Yeah. So now this is EV, EC, EFI at center. Now this is EFP, EFP. Okay. Okay, sir. So this is about the complete energy band diagram of a p-type semiconductor. Okay. Now from the knowledge of all this, we are going to write all the energy band diagrams at one point. Okay, please take a note. This is very important. This is for intrinsic semiconductor and this is for n-type semiconductor and this is for p-type semiconductor. So this is EC, EC here and EC, EV, EV, EV. So first I will write up to that. So this is EC, this is EV, it is EC, EV, EC, EV, and one more, this is intrinsic semiconductor, it is intrinsic semiconductor, intrinsic semiconductor, and this is n-type semiconductor, n-type semiconductor, and this is p-type semiconductor. I am taking p-type semiconductor. Now here first I am going to draw the intrinsic Fermi energy level. Here intrinsic Fermi energy level is approximately midpoint. So it is approximately midpoint. Approximately midpoint. So same here. Same here. Approximately midpoint. So this is going to be EFI, intrinsic Fermi energy level. EFI. So and EFI. Now this is intrinsic semiconductor. No need to draw any line because all are completed. This is n-type semiconductor. Now we need to draw its energy, its Fermi energy level. Its Fermi energy level for n-type semiconductor is by adding n-type impurity. See, Fermi energy level is nothing but a average energy level. Okay, by adding n-type semiconductor, n-type impurity to the intrinsic semiconductor, number of electrons in that is going to be increasing. Once number of electrons are increasing, its average energy level also increasing. That's why it is here. Is here. This is the Fermi energy level of n-type semiconductor. Next, p-type semiconductor. Here, by adding p-type impurity, number of electrons decreasing. Already we completed. By increasing impurity, majority carrier concentration is increasing and minority carrier concentration is decreasing. So in p-type semiconductor, electrons are the minority charge carriers. By increasing amount of doping, minority carrier concentration is decreasing. Initially, this is the Fermi energy level. That means average energy level of an electron without doping. After doping, number of electrons are decreasing. Once number of electrons are decreasing, its average energy also decreasing. This is the average energy level of p-type semiconductor. Now it is EF. So it is EFP, EFP, EFP. Okay, so like this you can draw the energy band diagrams. Clear? And we have one more point in this. Now you may ask one thing. Okay, let us, I am taking n-type semiconductor. Okay, take that. So EC and EV. Okay, this is a n-type semiconductor, sir. N-type. EC it is, EV it is. Now, in case of intrinsic, its intrinsic Fermi energy level is at midpoint. Its intrinsic Fermi energy level is at midpoint EFI. So it's once, now I am going to adding some impurity. Case 1. I am adding impurity. Let us assume ND is equals to something. Now that ND value I am going to apply in first case 10 power 16 per centimeter cube. Second case 10 power 18 per centimeter cube. Third case 10 power 22 per centimeter cube. Okay, in first case, let us your energy band diagram. In first case, your Fermi energy level is just above that. This is the case. In first case, it's Fermi energy level. Okay, because of this doping, number of electrons are increasing. Once number of electrons is increasing, its concentration also, its average energy also increasing. So this is the Fermi energy level in first case. EFN in first case. Next case, you are adding impurity 10 power 18. That means you are increasing the amount of doping. You are increasing the amount of impurity what you are adding to that. Now it results, it is moving upwards. So let us close to this. This is the second case. It is also Fermi energy level of it. Okay. Now up to this, it is everything is fine because EF is always less than EC and it is greater than EV. But now once suddenly I am going to increasing the amount of doping more 10 power 22. Now this Fermi energy level is moving above the conduction band. This is the third case. It is the Fermi energy level. EFN in third case. This type of semiconductors are called degenerative semiconductors. Degenerative semiconductors. This type of semiconductors are called as degenerative semiconductors. Okay. Mass action law is not applicable to degenerative semiconductors. Okay. So mass action law is not applicable to degenerative semiconductors. Okay. Now let us we concentrate only on third case. So for my easy understanding, I am going to erasing this. So I am going to erasing this. Yeah. Fine. Now, see, from Fermi Dirac distribution function, from Fermi Dirac distribution function, we learn This is conduction band, this is valency band. Okay, all energy levels in valency band are completely filled at 0 Kelvin. All energy levels are completely filled at 0 Kelvin in valency band. And all energy levels in conduction band are vacant. This is about your energy band diagram of intrinsic semiconductor at 0 Kelvin. Once you added FDD, once you apply FDD to this, now here we taken Fermi energy level. The energy levels below Fermi energy level for E less than EF, all energy levels are completely filled, and for E greater than EF, okay, all energy levels are completely vacant. All energy levels are completely vacant. So that is the meaning of this plot what we completed early. This is F of E and this is E. Here it is EF. This is at 0 Kelvin. Now once you are applying this one to this, what happens? Okay, at 0 Kelvin what you are expecting? At 0 Kelvin you are expecting all energy levels less than EF, and in valency band should be completely filled. So valency band is completely filled. It is. This is energy gap, sir. So FDD is not applicable to this. Energy gap it is. FDD not applicable to this. Don't draw lines here. Now, some portion of conduction band also less than the Fermi energy level. That means this is also filled energy level. Here also some filled energy levels, even at 0 Kelvin. But at 0 Kelvin you are expecting conduction band is completely vacant. Conduction band of a semiconductor at 0 Kelvin you are expecting completely vacant. No energy level is going to occupy by any electron. That is what we are expecting. But in this case what happened? Some portion of energy levels are occupied because of high amount of doping. Okay. So above this vacant. Okay. So this is the special case. You may ask one thing. Sir, you are adding like that. Taking you've taken a milk and adding sugar, 1 spoon, 2 spoon, 3 spoons, 4 spoons, like that. What is the use of it? You will get from in this case, first you are given 10 power 16 you added, after that 10 power 18, after that you are taking 10 power 22. You are going to increasing level by level, you are going to increasing the amount of doping. Then what is the use? Say this. By using this semiconductor, by doping this much, the semiconductor what I get, that is I am going to using to design a PN junction diode. By increasing amount of doping, whatever the semiconductor I get, I am going to use that to design Zener diode. And heavily doped semiconductor what I has, this case, in this one, I am going to use that to design a tunnel diode. That is this simple. Now, taken a bowl, in that I taken a milk. If I add 1 spoon of sugar, it can be used as a PN junction diode. That material can be used for designing of PN junction diode. If you are adding 1 more sugar, 1 more cup of sugar, 1 more spoon of sugar in this sense, more doping. You can use that one for designing of Zener diode. And 1 more spoon. That means now I am adding 3 spoons. More doping. Now I am going to use that one for designing of tunnel diode. Okay. So similarly, if you take the p-type semiconductor, okay, what happens? How it is looks like. Now we check it. In n-type, conduction Fermi energy level is entered into valency band, conduction band. Okay. Now in p-type, Fermi energy level is entered into valency band. See this. So this is a EC EV. Okay. Similarly, if I am going to taking heavily doping, let us take 10 power 22 per centimeter cube. In that case, your Fermi energy level is somewhere here, EFP. So this is our degenerative p-type semiconductor. In tunnel diode, we discuss about in detail about this. Now here all these energy levels are completely filled. Okay, actually according to semiconductor energy band diagram at 0 Kelvin, energy levels below EV has to be completely filled at 0 Kelvin. But here some energy levels below EV are not filled because of high amount of doping. So that is the difference between this one and regular semiconductor. Okay. Okay, sir. So far we done everything qualitative point of view. That means by increasing amount of doping, majority carriers is increasing, minority carrier is increasing, decreasing. By increasing temperature, minority is increasing, majority also increasing, but percentage of majority is less increment compared to percentage of increment in minority. Similarly, we placed energy levels, different energy levels we placed on here, the energy plot. Okay, next part, everything we are going to be representing quantitatively. Something, some equation we are going to be deriving for that. Everything we are going to deriving some equation. Everything we are going to be quantifying by something. This is something, this is this much, this is this much. So far we get something like that. Now I am going to quantifying, this is this much, this is this much. I am going to be fixing that. Okay, next. See, so far what we discuss is this one. EF is approximately at midpoint of the energy gap. In n-type semiconductor, EF is close to EC. In p-type, it is close to EV. Okay, in n-type semiconductor, by increasing the doping, EF is moving towards conduction band, and if doping is very high, EF is entered into conduction band. In similarly p-type, it is entered into valency band. These type of semiconductors are called degenerative semiconductors, and mass action law. Next class we go and discuss about that. It is not applicable to this degenerative semiconductors. Okay. So, and one more, already last class we completed this analysis. This is simple. Next, in charge neutrality we will discuss in detail about this. This is not right time. In charge neutrality we will discuss. This is important thing. Now, in any semiconductor, you can take any type of semiconductor, either intrinsic semiconductor, extrinsic semiconductor, okay, n-type or p-type, whatever it is, okay, you can take any type of semiconductor. Just electron concentration is equal to n is equal to nc into e power minus of ec minus ef by kt, and whole concentration P is equals to EV NV into e power minus of EF minus EV by KT. These are the equations for electron concentration and hole concentration in any semiconductor. Okay. Now, see, the electron concentration is Nc into e power minus of Ec minus Ef by Kt. In this equation, N is electron concentration. We know Ec is minimum energy level of conduction band. Ef is the Fermi energy level. K Boltzmann constant. T absolute temperature. And Nc is a density of states in conduction band. That means you are saying in energy band diagram, this is our energy band diagram. This is Ec, and let us take it is Ev. This is, you are saying it as energy band. Okay, energy band diagram. Energy band in the sense, so many energy levels are defined in this. So many energy levels are defined. Plenty of energy levels are defined. Now, the defined energy levels are how much density they are, how much close they are, how much density they are is represented by the term NC. Okay, NC is the density of states in conduction band. Similarly, for p-type semiconductor, whole concentration P is equals to NV into e power minus of EF minus EV by KT. So here NV is the density of states in valency band. Density of states in valency band. See this. It is the density of states in valency band. Okay, these are the values of N and P. So now on next class onwards, we are going to using these two equations to derive any equation. Okay, here we are going to derive the equations of intrinsic carrier concentration, intrinsic Fermi energy level, okay, different relations, energy relations. Okay, whatever the different energies here we are going to deriving all those energy relations. Everything we are going to be derived from the knowledge of these two N and P only. Okay, so these are the values of N. 2 into 2 pi mn star kt by h square whole power 3 by 2. By simplification you get this. So next class we verify all this. So please don't forget to subscribe this. Use my code VRAW10. Okay, and if you want the notifications of my classes, just click on this bell, notification bell. And one more, if you are interested, join in Telegram group to get the latest updates. Okay, and we are welcoming all the comments from your side. Okay, to strengthen ourselves, those comments are helpful to us. Okay, thank you, thank you very much. And once again, I'm going to be welcoming you all to the online, India's largest online platform, Unacademy. Thank you very much. Thank you, thank you very much.
తీసుకొచ్చిన
అని ఒకసారి చెక్ చేయండి దాంట్లో వస్తుందో లేదా అయిపోయిందో అది ఇప్పుడు చూడండి ఒకసారి ఆగిపోయిందా చెక్ చేయ త్వరగా